Welcome back to our session on introducing the JIDT toolkit. In this short video, we're going to look in some more detail at the code that's generated using our first example from the Auto Analyzer GUI, looking at some discrete data with our discrete plugin calculator. So we're going to examine the code that was generated. So what we can do here is either click on the panel in the GUI for the language you want to work in, or open the file that's automatically generated for you. And they're listed here. You've got your Java file at this location and the MATLAB or Octave and Python files in the Auto Analyzer directory. Let's have a quick look at that. So of course, we know that we can see the code in our tabs here. And as I say, we can also go to the code. For example, if you go to the Auto Analyzer directory, our MATLAB and Python files are right here ready to go. We can pull up, for example, the MATLAB file in our editor right here. Okay, and we can run these as well, as I pointed out in the slides. So we can come back to our Auto Analyzer location here. Let's grab a terminal window. So we can run the Java file by running run auto generated .shell, and I don't think I've set the executable bit here. We have not, so let's do that quickly. In Linux, in Windows, you won't have to do that. Okay, so now we can run the Java version of the calculation, getting one bit again, as we did when we ran it in the last video. We can also run, let's do Octave instead of MATLAB for ease. We can run our generated calculator, getting the same result. And then in Python, we can do exactly the same thing again. We can run our Python code and get exactly the same result. Okay, so that code's all there, ready to go for you. Now let's go through it in some more detail. Okay, we've just done this run here, so let's go through it in some more detail. First things first, we want to observe how the jar file, our library file, is pointed to by our code. In Java, this is done in the command line that runs the file. So if we look at our auto-generated shell file, shell script, let's just pull that up here. We can see that the jar file is referenced directly in our class path. We can also look at the MATLAB and Python code and see how the library is referenced there. So here in MATLAB, it's with the Java add path command pointing to the jar file. In Python, it's with these commands here, where we set the jar location, and when we start the JVM, it's supplied here in the command. Okay, so these are important because that tells Java, Python, and MATLAB where to find the library file. Okay, after that, let's have a look at the data format. Always with the JIDT toolkit, we are using arrays, whether they're one-dimensional for univariates or multi-dimensional for multivariate data. We're using arrays to represent our samples. So here for discrete data, we're using integer arrays. In Java, we use those directly. For Python and MATLAB, we're going to use native array formats there and convert from Java. I'll show you how to do that later in this video. So for one variable here, we simply have an array of values, and those entries represent different samples. The values take the range for discrete data, 0 up to the base, where, for example, the base is 2 for binary data. And we saw how to set the base on the GUI before. The array is indexed by a sample number or observation number, or if it's a time series measurement, the array is indexed by time. If we've got a multivariate time series, we're going to use a two-dimensional integer array now, where it's indexed first by the sample and then by variable number. Okay, so the row number here indicates the sample index or time. The column number indicates which particular variable we're dealing with. Okay, so for one sample, we have a sample for every one of our variables. Your data files can have comment lines starting with a percentage sign. That will work in all the different languages. If you're only using the data in Java or Python, you can also have a hash, but a percentage will work in all of the languages here. So let's have a quick look at the data file that we just dealt with to inspect what that looks like. So that was data, 2 coupled discrete cols. We'll have a quick look at that. You can see here we've got some comments up the top with a percentage sign starting, and then we've got 2 columns of data for many samples here. Okay, moving on. So how do we use the discrete data calculators? This flowchart explains that we have a number of steps where we construct the calculator, we initialize it, we add some observations in, we can do that multiple times, and then we can make a computation, and we can make various computations at that point. You'll see that I've indexed these as steps 1, 3, 4, and 5. Obviously step 2 is missing. That's not an accident. This is to align with the usage paradigm for our continuous data calculators, which we'll look at in our next session. That has a step 2, setting some properties that we don't strictly do for the discrete data calculators. Let's take these in turn. So I've shown you some sample code here that aligns with what we've got from the GUI. This is written in Java, but you can look at what's been generated in the GUI to see how these lines translate into how they're used in MATLAB and Python, but it's almost exactly the same. Okay, the first step here is to construct the calculator. Okay, when we construct the calculator, we provide some important parameters. When you generate the code from the auto analyzer, that will fill out anything you need in that statement. Okay, but if you're not using the auto analyzer, go and check the Java docs for what parameters are required in your constructor. I showed you in one of our previous videos how to find the Java docs. Here, the parameters for the mutual information discrete calculator are the number of discrete symbols per sample, which is 4, and the source target lag to compute the mutual information across. As I say, these are being filled in for us by the auto analyzer from the property values here. So we can find that line here for Java, coming down to this line as well. Sorry, this is Python. I'm showing you that's how we do it in Python using the J package call. In MATLAB, we do this using the Java object call, and in Java, we do it as I've been showing you before. It's a slightly different call here to what I've got on the slides. Okay, as I say, the constructor syntax is different for those other languages, and you can see that in the generated code. So our next step is to initialize the calculator. We do that prior to using it in the first place, or if we want to reuse the calculator. So we can reuse the calculator, for example, in a loop, which you can see by clicking all pairs. We can just construct it once and then reuse it over different pairs, and that clears the probability distribution functions that the calculator holds to get it ready for new samples. The next step is to supply the data to the calculator so it can construct the PDS. We do this with the add observations calls. This can be done multiple times, so you might have multiple trials, and you get some data from each of those trials, and you have to put it all together. You can do that with multiple add observations calls, as I showed you on the flowchart that we looked at a few slides ago. Now, importantly, if we're calling the calculator from MATLAB or Python, we need to convert the arrays into a Java native format. That's done for you with the auto analyzer using these different calls that are outlined on the slides here. We can see this if we flick over to the code. So we can see this in Python. Hasn't strictly needed to do it here. Sorry, it has strictly needed to do it. I just didn't see it. So here we're using a JArray call. In MATLAB, we're using a octave to Java double array call. Okay. Now, importantly, I'm actually showing you a bin calculator here. I didn't notice I'd switched over to bin instead of discrete. When we use the bin calculator, we're assuming the data starts as continuous, and that's why you're seeing this discretized call. That's why you're seeing the discretized call here. You wouldn't see that if I just called the discrete calculator. It's assuming the data is discrete already. Okay. Okay, so importantly for Python as well, we can use NumPy arrays. When we do, we have to export them to list for the discrete value calculators. It's not necessary for continuous, but we'll look at that later. So finally, we make our computation. Our results are always returned in bits for the discrete calculators. And here we saw that the result approached 1 bit because the destination was copying 1 bit of the random source across one time step. So this is the line for computing the average result. There are other computations that we can undertake here as well. We could compute the local or pointwise values, and that will return an array with an entry for every sample, or we can compute the significance look at the statistical significance of the value, and that's something that we'll talk about in a later session. So coming back to the flowchart again, you've seen that I've talked you through this now, how to run through these steps for the discrete calculator. Importantly, the GUI tool will generate that for you. Okay. There are more complicated things you can do. You can take the code and extend it. For example, if you want to add observations multiple times, the GUI is not doing that natively, but if you've got multiple data files, you might want to do that. You might want to add other things to compute, like the local values and so on. There are all ways that you can extend the code that the auto analyzer generates for you. So that's the end of our session on an introduction to JIDT. I wanted you to take a few things away from that, including understanding what the toolkit offers for information theoretic calculations in terms of both the measures and the estimators. I wanted you to be able to obtain and install the distribution, and in particular to use the auto analyzer, the most important demo, to make some simple information theoretic calculations on discrete data. We're going to look at continuous value data and more complex estimators in our next session. I also wanted you to understand how and where to seek further information, including from the wiki in particular and the paper that introduced the toolkit. So I hope we got there. If we're all in class together, obviously I'd throw it open for discussion now. Otherwise, I hope you got there and the activities that we've got helped you get there as well. So our next session, we'll talk, as I say, about looking at estimators for continuous data and how to use these in JIDT.